Alright, morning. Let's start lecture on Kalman filter. So here's a system, okay, a linear system. Okay, so the difference now is basically the system is contaminated with the process noise W, and is also contaminated with the sensor noise V. Okay, so the process noise and the sensor noise, both of them are Gaussian noise with a mean of 0. And W of k is a vector, so it's a random vector basically. So the covariance, okay, or the correlation for the random vector W, okay, is this. So basically, if G and K are not the same, it's a 0. Otherwise, it's just 1 for this Kronecker delta function. So if G and K are not the same, basically the two random vectors are independent from each other. Okay, yeah. The RW here is what we call the basically the variance, okay, of this of the matrix here. So sigma 1 for W1, sigma n for Wn, right? Yeah. So RW is a matrix you generally will select or you choose at the beginning of everything basically. Okay, yeah. And same thing for the V. If you just change this W to V, you get basically exactly the same kind of property. Okay, so this is RW and this is RV. All right, yeah. So these two basically serve as the variance matrix for the noise. Okay, so for example, WK, as if we write like this, is because it's saying it's a Gaussian noise with mean of 0 with variance matrix of the RW there. So V of k is the same thing. Okay, yeah. So RV RW you will give and when you start to implement your Kalman filter. If we let x hat of k be the estimate of this x of k, okay, then the estimation error is basically x of k minus x hat. Then the objective is not to minimize the error. The objective is to minimize the error covariance matrix. Okay, yeah. So in the previous observer design or previous optimal control design, your objective is to minimize a deterministic quantity, right? Yeah. So this one here, because there is a noise in it, so what we're doing is we're basically minimizing the covariance of the matrix here. Okay. Yeah. So this type of control here. So first, what we're doing is a so-called predictive type of a Kalman filter. Okay. Yeah. So predictive Kalman filter, in particular, when it comes back to this error covariance matrix P. Okay. So what we typically write is, so this P of k plus 1, it can also be written as P of k plus 1 and then k. Okay, so vertical line and then k. So what does this mean basically? This is a similar idea, the predictor, right? So you're predicting the k plus 1 moment value with the previous knowledge, right, obtained from the case moment. Okay, it's like the conditional probability, that type of writing, right? Yeah. Okay, so first what we're dealing with is a predictive type of Kalman filter, right? And then we'll deal with a current type of Kalman filter, and that's the kind of a Kalman filter that that we will implement. Okay, yeah. So the idea is to minimize P of k. Then what we need is, okay, so we need to obtain what is basically this E of k plus 1, and then we're going to plug it into this bracket here, right? Yeah. E of k plus 1 is x of k plus 1 minus x hat of k plus 1. So x of k plus 1, okay, this is the system. Okay, and this one in here, x hat of k plus 1. This is basically taking as as a same model as our observer design. So x of k, the model for this x of k is this. So equal to the system matrix, and this, no difference. And then use a feedback gain. This is basically, you can call that observer gain, or here we call that the common filter gain. Okay, and then times, I'll put it down the bottom here, plus this guy, and then times c x of k plus v of k minus c x hat of k. Okay, yeah. So this quantity is y of k. Your actual, basically, this is the actual system output, and this quantity here is y hat of k, right? So so this is from the system. That's basically this one here. X hat of k is from here. Okay, yeah. Then the rest of the thing is purely algebraic now. Plug this x hat over here, so plug in here, solve for e. Okay, so then we get our e, which turned out to be g minus kc e of k plus w of k minus kk and v of k. Okay, so this is the error. Okay, so this is the estimation error. Apparently, estimation error is a noisy signal, right, with w and v in it. Okay, so then we plug it into the P matrix. Expected value okay, yeah. So you basically you plug in this quantity over here and here. Okay, you take a transpose, of course. Okay, so that's your P matrix here. Okay, yeah. So to simplify the writing at this stage a little bit here, so we can let a temporary quantity n of k equal to this portion. Okay, equal to this portion here. Okay, yeah, like this. Then if you do the substitution at here, and you do the transpose, and you do the multiplication, and you expand things out, we get our P of k plus 1 now, okay, this quantity equal to, okay, this one here. So g minus kc expected value e of k e transpose of k, then g minus kc transpose, like this is the first term. The second term is g minus kc times e, okay, e of k n transpose of k. Second term. Third term, expected value of this, and then times g minus kc transpose. The last term, okay, so your covariance matrix, okay, your error covariance matrix turned out to be this one here. Okay, yeah. Again, the k here, this one here is a common filter gain. Okay, yeah. Okay, so looks like there's pretty long expression at here, right? But if you recall the definition of n, which is this guy at here, this is a noise. So the expected value of this, basically this is correlation here. For this one here, this is actually because a lot of term here will all become 0. E and N, they are independent. N and E, they are independent. So this and this, 0. 0. And this is also going to be 0. Okay? Yeah. So for the proof of this, okay, you can look at my lecture notes. Okay? So I'm not going to prove this out. So there is a one-page proof here for this one here. So you can look at that. All right? Yeah. So basically, in the end, your P of K, the error covariance matrix. Remember the name of it. It's error covariance matrix. Just this guy here. All right? Yeah. Oh, I'm sorry. No. What I'm doing here? Yes. This guy's not 0. If this is 0, then it's gone too simple. Okay, this guy's not 0. Well, it makes sense, right? Because this is n transpose, n times transpose, it's own transpose, right? So the correlation, there's definitely correlation there, right? Yeah. So what is this guy here then? I'll just write down the solution for this one here. That's what I mean. When you look at the solution, you can look at the proof from the textbook here. So for the last term in here, okay, the expected value of this is equal to RW plus the common filter gain K times RV times the K transpose. Okay, so this is the results of the last term here. For proof, you look at the lecture notes. Okay, yeah. So then what does that leave us for the error covariance matrix? So only two terms. First term is this, and plus this term here, right? Plus this term. And you look at the first term in here. What is this guy here? Expected value for error times error transpose. Okay. And what's this term? And what is this guy? So what's this term? It's P of K, right? So that basically gives us P of K plus 1 equal G minus KC, okay, P of K times G minus KC transpose plus this RW plus K RV and K transpose. Okay, yeah. So this is basically the results of this part of the derivation at here. Okay. So your error covariance matrix, right, is what we're trying to minimize, and we derived that our error covariance matrix is this part, is this. Okay, yeah. Okay. Now, this is very much look like the common field recurrent equation there. But it's not exactly the same thing. But this is basically a difference equation for P of K then, right? Difference equation. Okay. Yeah. Now remember what we're doing here. Okay. What we're doing here, the objective is to minimize P of K here plus 1. You minimize this. When you minimize a function, you minimize function with respect to a certain variables, right? You know, basically at what variable that function will become a minimum. So you look at this function here. What P of K of the function for the P? It's not really a function, but it's a matrix here. The P is actually a function what? which one is a variable here? G is not a variable. RWRV, they're not a variable. So the only variable is which one? Is the common filter gain K, right? That's what you're designing. So then if I wanted to minimize this guy here, then we do what? We do the first derivative test. We take the partial derivative of this with respect to your variable K. Okay? And then you set it equal to 0. And then you solve for the stationary point. Okay? And that solution for the stationary or the critical point is basically the solution for the K. Okay? Yeah. You have a function f of x, you set the first derivative equal to 0, then the solution for the x is the stationary point, right? Is where the minimum is. So then what we do is basically now we're basically taking partial derivatives with respect to K, and also the same as the other side as it is. Okay, yeah. So here is what happens now. Let's say I'm gonna let this quantity to be D, and this is D transpose now. Okay, yeah. So partial derivative, right? Yeah. There are two terms. So one is this, and the other is this. And then let's see for the first one, the partial derivative of d p of k d transpose over partial k. Okay, that's the for that term over there. Okay, we need actually use a chain rule right here. So partial derivative with respect to d first, and then partial d over the k next. Okay, yeah. So you get basically from here you get negative 2 g minus kk, well, k here. So that's a c p of k plus c transpose. Okay. So k itself is basically still, I'm just neglecting the k. If you give enough number of steps, it will converge, but it'll take a few steps basically for k to converge to something. Okay, yeah, that's that term there. Okay, and then for the last two terms, okay, this is constant with respect to k, so it's gonna be gone. So the last term, the partial derivative is back to k, and that one's easy. So k RV k transpose over k. So this is basically just 2k and RV. Okay, so 2k RV. All right. So overall, the partial derivative of the p with respect to k give us what? So this guy plus this guy, that's the partial derivative, right? First derivative. Then you set it equal to 0. So we end up with this basically negative 2 g minus kc p of k plus c transpose, and then plus 2k RV and equal to 0. Okay, so we end up with this quantity here for the first derivative test. So 2, 2, you can get rid of them, and then we can solve for the k, from this equation right here. Solution for this k is g p of k, c transpose, and RV of k plus c p of k c transpose inverse. Okay, yeah. So that's the solution for the k. Remember what the k is? This is the common filter gain, right? Common filter gain. Where do we use the k again? We use that over here, right? Use that in our observer model. Okay, just like typical observer, full order or reduced order, right? You have a observer gain, right? Yeah. So Once we get the k now, what we can do is we can sub this k right back into that P of k plus 1 matrix, that's expression over here. Substitute back into this guy here, okay? This equation here. Then we can obtain the minimum value, right, for this P of k, the function. Okay, yeah. So if you do that, and with some arrangement, you will be able to get, okay, this P of k plus 1, okay, equal to RW plus G P of k G transpose minus G P of k C transpose RV C PK C transpose inverse, and running out of place, then C PK G transpose. Okay, yeah, that's the last results for this P of k plus 1. Okay, yeah. So basically, what you're gonna do is you're actually basically solving this equation and this equation at this same time. Okay, iteratively. So how do you solve? For example, you start with a P0, right? Start with a P0. The P0 is an initial value you picked. So what is the P0, right? P, always remember, P is the error covariance matrix. So P of 0 basically is the expected value, right, of the estimation there. Okay, and in our particular case, we assume that, okay, we know the we have the P of 0 is this. Okay, so this is going to be your P of 0 at here. Okay, it's going to be P of 0. So it's the error covariance matrix. It's the covariance matrix actually between your initial condition, okay, and the average value of that. Okay, so basically it's a confidence of how much you have for the initial value x of 0. Okay, yeah. So you can set this guy to be a certain matrix. So you usually, if you take a very large quantity of this matrix, for example, you take 100, 0, 0, 100, like this. Okay, yeah. And the larger quantity of this is, then that means you have a less confidence in terms of the initial condition x of 0. Okay, yeah. So that's how you can set P of 0. Once you get a starting point at P, then you can solve for K. Then you substitute K here, and you can solve for the P, the next P. So the next P, substitute back here, solve another K, and then you substitute back over here, you'll solve for another P. Okay? Yeah. So that's basically the idea of this predictive type of a Kalman filter here. Okay? Yeah. In a more practical case, what we implement is actually the next type. Okay, is called the current type of a Kalman filter. Okay, the current type. So the current type of Kalman filter is very much basically. So how many observers do we learn? We have 4 observer, and there is another one. And I said it's required for graduate students only. It's called what? The current type of observer, right? The current type of observer. So it's the same kind of a idea at here. Okay, same kind of idea. So what we do is we do this. We let x hat of k plus 1 and the k for this guy here. So see, Now the writing is slightly different now, okay? So x hat k plus 1k. So this one here is be the estimate of x of k plus 1. So we'll let this guy to be the estimate of k plus 1. But this is only based on, okay, it's only based on information, okay, up to, okay, instant k. Okay, so you see, so this is basically x as estimate of k plus 1, but only based on information up to instant k. Okay, so that's what this notation means. Okay, yeah. And then consequently, then what we have is, okay, we have basically first is basically this predictive estimate model. Okay, predictive estimate model, and this model is x hat k plus 1 k equal g, okay, x hat then k plus h, okay, u of k. So this is the predictive model. Now over the left side here you have a notation here is basically it's x hat k, right? X hat k. So what this one here is, you should compare to this definition here. If this x hat k plus 1k is the estimate, right, based on the information only up to the instant k, right, then we have also this notation now. So x hat k plus 1 up to the information k plus 1. So then essentially what happens is you should consider after the prediction, and then here comes your updated measurement y of k plus 1, right? Then we can use this new information k plus y of k plus 1 to update our estimate, this guy, to update to what? To update our prediction here, right? To become this x hat k plus 1 k plus 1. Okay, yeah. So this guy here, right, will be an update, right, based on the current, okay, measurement. Y of k plus 1. Okay, yeah. That's why it's called current type of a common filter, right? Then what is the model for this x hat k plus 1 and k plus 1 then? So this is basically the current type of same as current type of observer. It's this x hat k plus 1 equals x hat k plus 1k plus the common filter gain k times the difference between the actual output minus estimated output, okay, based on the prediction. Okay, yeah, that's your update model here. So this is a predictive model, and this is the update model at here. Okay, update model. Okay, yeah. Now, in terms of the objective now, as before, we basically also wanted to minimize the error covariance matrix. So the error covariance matrix at here, so what we do is we define our error, okay, to be the difference between the actual value of the state minus, okay, the current, okay, minus the value from the update model here. Okay, that's the error here. Then your error covariance matrix, okay, the P would be the expected value of E like this now. Okay? Yeah, like this. That make sense? Yeah. So let me give you a very simple analogy at here. Okay. So let's say let's consider scalar. Let's consider a scalar case. Okay. If you have a scalar case, it's just one state variable, and you find your error. You have a error. You have find an error. Okay. And this guy has a standard deviation sigma E, which is, let's say, 0.3. Okay. So this is the standard deviation of this guy here. And now your you know that the average, okay, of this let's say x of k is 1. Okay. And you know that your x of k will vary between, okay, has a positive and minus, okay, 3 times the error at here. Okay. So what would be the range, basically? What would be the range of your estimation now? The range of estimation would be what? So basically just 1 plus minus 3 times this, right? Yeah. So you have basically you have the actual value is 1, and then your estimation is basically is varying among this along this range over there, right? Yeah. So the idea is still to minimize this guy here, okay? To minimize this. So then you can guess now what to do. Basically, you plugging the error into this matrix, into this expression right here. Then you expand. You take a partial derivative. Then you solve for the common filter gain, right? It's the same idea. Okay. So I'm gonna go through that part anymore. So the results that we get, right? Okay, is basically the information I listed over here. So I'll just skip part of some information in here. All right, I have a handouts here. So the results, basically, it's this table at here. Okay, the results is essentially this table. Okay. So based on this table is how we actually program our common filter. Okay, so if you look at the table here, okay, yeah, if you look at the table here, let's just quickly go through the idea of this implementation. Actually, as I said, the derivation seems to be a little bit taunting here, but implementation, actually, there's only going to be 1, 2, 3, 4, 5, maximum 5 line of code if you do that in MATLAB. Okay, yeah. So what does it do is basically you have this is your system model, right? Here's system model, and here's your initialization. Okay, so you initialize certain estimated initial condition and also P0. Then we use our predictive model. Basically, this is what we call the propagation part. Okay, to calculate x hat k plus 1k. Then you calculate this p of k plus 1k. So this is also prediction here, right? Yeah. So the p of k plus 1k is based on p of k plus 1k and also RW. Then we update and then we calculate basically the common filter gain, capital K. Okay. Once you get this, then we do the next one here. That's basically the part of the current, right, from the current type of a common filter. So you do a measurement update, then you calculate the error covariance matrix, capital P. So both of this, so look at it, both of these are error covariance matrix, right? What's the difference between these two? I mean, of course, this is k, this is k plus 1, right? Yeah. But from definition point of view, this guy here is the error covariance matrix, right, between the actual value and the current. Okay, x hat k plus 1k. And this guy here, okay, that p of k plus 1, the k, this guy here is it's still the error, but it should be between x of k plus 1 minus x of k plus 1, this is x hat, and k. Okay, so that's the difference. Okay, yeah, so they are both errors covariance matrix, but the two errors are slightly different though, huh? Yeah. Okay. So the implementation wise, all you need to do is basically to implement the system, implement this 5 line of code here, and here you will have the common filter gain. Yeah, the common filter basically for the system. All right. Yeah. So I'll show you how simple it is to do the implementation. You can also take a look at lecture notes here. See, for example, right? Here's the model for the double integrator. We have used that several times already. Okay. So now we insert a certain noise into the system. Okay. Then when it comes to the simulation, right, or calculating the gain. So here's basically this is system here, initialize RW, and the implementation at here 1, 2, 3, this line code. It's essentially just what you have in the table. Okay, so what you have in the table here. Okay, then at the end, I plotted, okay, the common filter gains. So here is a system of order of 2, right? Then there are 2 basic states we are estimating. So the gain k has 2. It's a vector, basically it's 2 by 1, right? It's a vector 2 by 1. Okay, yeah. So that's why you see it. One is green, one is blue. Why there's 3 here? Basically, we and in this simulation here, it took a consideration of 3 different ratios of RW and R over RV. Okay. Remember, what does RW represent? It's the variance for. There's the 2 noises. They're both noises, right? One is noise for what? RW is the noise for the process, and RV is the noise for, see, RW is the variance, the noise for the process, and RV is the noise for the sensor, right? Okay? Yeah. So I want you to look at this one here. So let's take some not so mathematical, just the common sense analysis at it here. Okay. Why is that when the ratio of RWRV is increasing, that the gain is also increasing at here, right? So the common filter gain is increasing. Okay. Again, you gotta basically again to think about where does the common filter gain show up in terms of your common filter. It's here, right? It's this little location here. What do you use the common filter gain for? You use it to multiply with what? With the difference between the measurement, actual measurement, and the estimated measurement, right? Okay, yeah. So basically, it's like your pole placement. So you have a gain k. What do you use that k for? The k times what? Oh, that's not quite right. That k used for time the feedback x of k, right? I mean, in the observer design, it's the same idea, right? You have the k. You have a gain k, observer gain, then you time that, the difference between the observed value, right? Okay, yeah. So
if we had like high measurement noise, like our sensor had high noise, we want to boost our gain, right? So we get less.
Exactly. So if you let's think about that. So RW over RV, right? This is a measurement. This is a process noise. This is a sensor noise. So if you recall that diagram, basically, system noise or process noise, basically it's a noise goes into the system here, right? Sensor noise is the noise goes into the sensor. So basically, imagine yourself there's a sensor at this location, okay? Then it's going to be contaminated by the noise, okay? Like this, okay? Yeah. So if you think of this ratio right here, if RW is let's see, not necessarily much greater. So let's say if RW is greater than RV. So what does that implicate? That means which noise is worse? Which means what? If this is greater than that, so the process noise, right, is more noisy basically. Okay. So the process has more noise at here than RV, okay, than RV. Or RV, let's say maybe RV is bigger, right? So RV is bigger. And what you're doing is you're doing the estimate, right? Your estimate has to be based on the information here. So now you know as a user, that the process is more noisy and the sensor is more reliable. Okay, relatively. That makes sense? Yeah. So then, if the process is noisy, the sensor is good, and your K, common filter K, is applied to basically whatever the sensor is here, right? So then you will be basically more confident, and you want to have a good estimate. So then you'll be more confident. Let's give a bigger K basically, right? Give a bigger K. Okay, so. Okay. Yeah. But on the other hand, if RW is less than RV, so which means what you know is my sensor is contaminated with much more noise. So what would you do in that case as a typical things? Would you still try to recycle that information from the sensor as much as possible, or would you just reduce the implications right from that? So you wouldn't basically use that information as much as possible anymore, right? And which means you wouldn't use a bigger K at it here, because if it's a bigger K and the sensor is so noisy, then what does the bigger K do now? All it does is just amplifying the noise now, right? It's not doing any good. Okay, yeah. So that's basically the idea. Okay, yeah. And when we after the simulation, you can easily try that. You'll see the effect of this RWRV. So basically, always the first time when you design a computer or when you design the estimation, technically speaking, you need to have a good estimation of the variance of the process noise and the variance of the sensor noise. Okay? So sensor noise, generally sometimes the manufacturer sometimes are good ones. They could give it to you as to some specifications. Okay, yeah. But process noise, a lot of time, it also depends basically. You have some statistical approach to estimate RW and RV. Okay, yeah, or basically to estimate the variance of a certain noise signal, right? Yeah, but that's usually what you need to do at the beginning. But you can always basically try and error. So if this is actual system, I can always play around with RW and RV and then look at the response of the system. Okay, yeah. Okay, so I don't think I'm gonna. Let's finish all the material first, okay? And then I can use one lecture probably to show you how to implement the common filter, which is the diagram that I gave it to you, okay? Or the simulation that we do here. Let me finish one thing here, and then I'll come back to the diagram. Basically, this guy here, okay? And I'll show you why this is a realization of the table that you have here. Okay, it's basically a realization of this guy here. Okay, yeah. Okay, so one more topic. Okay, or two more topics. The last one here is right. So there's predictor type, there's current type, and then we have the so-called steady state common filter. Okay, steady state common filter. So what does this one do is basically, see, if you look at this current type of common filter, I mean, this is basically you do iterations, right? Okay. Then steady state basically means when your k goes to infinite, then you will end up at the steady state common filter. All right? Yeah, that's what it means here. So if k goes into infinite, if this small k goes to infinite, then the common filter gain k will become a constant. Okay, will become a constant there. Okay. Then the formulation of from the table will just become capital K equal to P. You can get rid of all the K now. C transpose RV CP C transpose inverse, and P equal to RW plus GP G transpose GPC transpose RV CPC transpose inverse CPG transpose. Okay, or just simply RW plus GPG transpose minus G times K times C times P transpose. Okay. Yeah. All right. To calculate the K, so I'll show you how we calculate the K for a simple system. But if you want to use if you're going to use MATLAB, there's this DLQE command. You can make use that to calculate your common filter, basically. Okay, gain K. okay, for this guy here. A proper usage of this DLQE, you can find that in the lecture notes, but let me just maybe. Yeah, maybe I'll just show you what to do at here. Okay, so I think it's a little bit confusing actually. If you have to use it properly, if you want to use the DLQE. So here's the system. Right, this is the system here. Then, when you apply this DLQE, what you need to do is you need to have this RW and RV matrix. Okay, you need to have these two matrices. So those are the two variance matrices, right? Remember those two. Either you just arbitrarily assign certain value, or you maybe get it from estimation or identification. Okay, yeah. Then here you need to think of yourself. There is a identity matrix at here. So let's say if you're n by n, so this is 1 basically up to 1 identity matrix like this. Okay, yeah. And then when you apply this DLQE, so here's your apply here basically. So DLQE, okay, you give the G matrix, give that I matrix over here, okay, and the C, and then RW and RV, the two variance matrices. Okay, yeah. What this one return, you can let it return a number of things. You can just let it return the gain K, that's one thing. You can also let it return a couple of two things here, P, Z, E. Okay, you can also let it return this P, and this is Z, and this E. So what are they then? This P, okay, is basically the Riccati solution. It's this guy here. So P is error, okay, x hat k minus 1 minus x hat k minus 1 minus x transpose. That's the P. Remember there are two error covariance matrix, right? In this table that I have, remember there are two error covariance matrix. This one, right, that the P from return from DLQE is this guy here. Okay, is this guy. And the second one, the Z, this Z right here is the Z here is this. Okay, from the DLQE. Okay, so that's what these two for. Okay, so the Z is the expected value x hat k minus x hat k minus x. Okay, yeah. The E at here is the eigenvalue of the closed loop, okay, based on this common filter here. Okay, yeah. So the E at here is the eigenvalue, which is G minus GKC. Okay, so that can be derived, and if you want, I can show you. Okay, yeah. So it's the eigenvalue of this guy here, right? Yeah. So that's how you use DLQE. If you don't care of a PZE, you can just let K equal to this. That's it. Okay. Yeah. All good? Okay. So let me show you an example right here. Okay. Of using this steady state, okay, common filter here. Okay. Yeah. So let's say I have a scalar system. So here's a scalar system with a W and a V. Okay. Process noise for sigma W square 0.5, sigma V square is 2. Okay. Yeah. Can you calculate the value of the common filter gain K for the steady state one? Steady state optimal gain, basically optimal common filter gain. So what is the capital K here at steady state? Right? Yeah. So what do we do? Right? We basically make use of these two equations. Okay? Make use of these two equations. So for these two equations, how do we make use of that, right? In order to calculate the K, I need the value of a P, right? I need the steady value of the P. So we probably need to calculate the P first. Okay? Yeah. So from here. Okay. So based on this equation here, what is the value of RW? What is the value of RV then? Given this question. What's RW? What's RV? Yeah. Right? Okay. Yeah. Okay, so then my G matrix at here is 0.5, H is 1, C is 1. Then my P matrix, if I go back to my P matrix here, it's RW plus GP, G transpose, GPC. So just plugging all the numbers into this guy here, right? So now what is P now? So P is an RW. Yeah. So P is RW is 0.5, and 0.5 G is a 0.5, and then times 0.5. So transpose of scalar quantity, no change, and then 0.5 times P over 2.5 plus P 2 plus P times P 0.5. Okay, so if you plug into that equation, and you get this expression here. Okay, get this expression. So this expression here, there's a P on both sides. So how do I solve for the P? So basically you can simplify everything, and you can multiply this 2.5, 2 plus P to this side here, right? And then sort out things, cleaning out, and get rid of the whatever common terms. So you will get P squared plus P minus 1 equal to 0. Okay? You would get this. This is a quadratic function, so you can solve that easily. So that has two solutions. Okay, that's two solutions. And which one are you going to use? You're going to use the negative or positive one? Can P be negative? The question is, right? Yeah. So you're going to use the positive one here. Okay? Yeah. So after you get the P, then you solve for the K. So the K is PC transpose RV CPC transpose inverse. So plug it in, you get P over P plus 2. And that's 0.2361. Okay? Yeah. So that's basically for steady state one, giving a very simple system, scalar or even it's a 2x2 system, okay, you should be able to calculate, okay, using these two equations right here. Is that clear? Yeah. Okay. Okay, so last point, okay, is so-called linear quadratic, okay, Gaussian, okay, which is LQG control. Okay, yeah. So Kalman filter is just a filter, right? So what does it do? It basically gives you the information of your state variable x of k. And it's up to the user as to what you do with the estimate. That makes sense? Right? Your ultimate purpose for the control here is to control the system. So your ultimate purpose is to make use of the estimate for your controller. Right? And the controller, we have learned different ways of controlling the system. And pole placement, LQR control, right? That's one thing we learned. So the simple idea is basically when you combine the Kalman filter and LQR together, you get this so-called LQG control. Okay? Yeah. So let's say if this is a planet here, okay, and here's your Kalman filter at here. Okay? Yeah. The plant is probably contaminated with the noise. Okay. Say W of K here. Okay. And then with the sensor noise V of K, for example. Okay. Yeah. So the Kalman filter will give out X hat, right? The Kalman filter will give out X hat based on what? Based on your system output and okay, the input. Okay? Okay, and the input. Okay. So then the X hat that you obtain here, if I give it to basically an LQR at here. Okay? So what's the nature of LQR? The whole idea of LQR is basically trying to obtain what? A K, right? A K, another K, well, same, different K now, right? From this Kalman filter here. And what do you use that K for? You basically use that K negative K times X hat, right? To generate to what? The U at here, right? The U at here. Okay. So this structure here is basically, simply put, it is the LQG. Okay. Yeah. Again, this is a regulation, right? It's a regulation at here. Okay. And you can expand that using that one of the lecture that we had in the previous lecture, basically to make it as a reference type of LQG. Okay. Tracking type of LQG here. Okay. Yeah. That makes sense? Yeah. So take a look at one of the MATLAB example I'll upload. Okay. Maybe I'll show you this example here. Okay. For the LQG. Okay. Yeah, here. So for this example here, this is actually one of the course project that I did when I was as a graduate student. So basically, it's a system that we call called a gyroscopic system, and that system, you know, gyroscopic, right? So basically, there's a spinning disc, okay, and you can hold the disc. The nature of the gyroscopic is basically when you have a disturbance or a change of orientation, and then the gyroscopic, the system, try to maintain its orientation, you know, the stability of that, right? Yeah. And what the purpose of that system is to do the modeling of the system and to design a controller to bring it back basically as not as using the nature of the physics of the nature here, to bring that to the equilibrium position as soon as possible. Okay, so that's the regulation problem, and the other problem is basically to sort of to control it, the disk, to go to a certain orientation angle, right? And that basically is what this example is here for. The ABC matrix and the other matrix here, they are all what's this B1 here? Remember, they are the matrix basically from the system identification. So the first step is do some system identification first. That's actually one of the lecture hopefully I can cover before the end of the term. Okay, yeah, and then design LQG basically. Okay, for based on this model here. The controller designed here, it's basically the same idea as I introduced from the previous lecture. So the reference part is the LQR referencing, and then plus the common filter gain. Okay, yeah. So you can take a look at this this MATLAB file, and I'll upload that to the here. I think if you wanted to implement this one here, I think you probably need to look at it, how do you input. But there's some offline calculation you may need, basically to get the steady state value of some of the parameters there. Okay, yeah. So talk to me if you are interested. All right, yeah. But if you run it, basically, this is what happens here, because the noisy system. Do you remember which one is which now? There's one basically. Apparently, it goes to the steady state, goes to the step output to responsivity here. But one of them is the estimate, and the other one is the actual, basically. All right? Yeah. So that's the idea of basically making use of the common filter. You're not just extracting information out, but also you are making use of the information to control the system. But for many robotics applications, for example, when you have a mobile robot, when you have a quadruped, sometimes you don't really actually use for any control purpose. You're just actually trying to extract the information out. Okay? Yeah. So, for example, when you have a target, you throw the targets out, right? Often in time, there's common filter application is you're trying to use our common filter to estimate the trajectory of the target. Okay? So you can also do many other things, you know, behind this idea of the common filter. Okay, yeah, even face identification, even I don't know. There's some other you can also get a quadruped from the accelerometer. You can get the actual Euler angles. So it's a very, very useful application. You know, it's so far I think it is the mostly cited paper for the common filter. Okay, yeah, in terms of the engineering applications. Okay, yeah. So I think I'm going to stop here and make use of the next lecture. So bring your computer here. Okay, we'll implement that MATLAB Simulink. Then you actually basically you just bring it into the lab and then change your model, change your system model, right? But keep the common filter part. Then you can implement.
Is there a project due next class?
Yeah, that's a good question. Not next class. Next class is 27. Sorry. Next class is 8th, right? Yeah. So I'm actually thinking pushing the project to maybe 17. so you can have a little more time to do a few more experiments. Okay? Yeah. Is that okay?
Yes.
Yeah.